Last time we left V as 3, minus 2, one object, drawn twice as an arrow and as a column. Put that arrow where it belongs, 3 along, 2 down. That lands you in the bottom right quarter of the plane. Here's what nearly everyone believes about that quarter, and it's a reasonable belief. The space is the room. The vectors are the furniture. You've got a flat plane, and arrows sit in it, and asking whether a region of the plane is a vector space sounds like asking whether a room is a room. That quarter goes on forever, and it's full of vectors, every one of them perfectly well-behaved. And it isn't a vector space. Scale V by -1. Minus V is -3, 2, up and to the left, which puts you outside the quarter entirely. Nothing about V changed, and the arithmetic was the same arithmetic. The set failed a rule. Grassmann built his whole theory out of rules with no picture attached. This is the cost and the payoff. So if a region this large can fail, what exactly is the test, and how few rules does it take? A vector space is a non-empty set V, satisfying 3 conditions. First, non-emptiness, the 0 vector is in V. Second, closure under addition. If U and V are in V, then U plus V is also in V. Third, closure under scalar multiplication. If V is in V and C is a scalar, then CV is also in V. Look at the third one again and take C equal to 0, and you get the 0 vector. So closure under scaling drags the 0 vector in whether you asked for it or not. It's a consequence, not a favor. A subset U of V is called a subspace of V if U is a vector space on its own. The plane you've been drawing on is R2. Three-dimensional space is R3, and the number line is R1. More generally, Rn is all vectors with n real components, and every one of those passes all 3 conditions. Now take a line that doesn't pass through the origin. It fails immediately. There's no 0 vector anywhere on it. Here's a subtler failure. Take the second and fourth quarters of the plane together, the 2 diagonal wedges. RV 3 minus 2 sits in the fourth. Bring in a vector P with components -1 and 4, and that one sits in the second. Add them. 3 plus -1 is 2, and -2 plus 4 is 2, so V plus P is the vector 2, 2. Up and to the right in the first quarter. Outside the set. The quarter we started with failed scaling, and this one fails addition. Different rule, same verdict. So which subsets of three-dimensional space actually survive all 3? Hermann Grassmann was a schoolteacher in Stettin. In the 1840s, he published a theory of extended quantities far more general than anything Hamilton wrote. Almost nobody read it, and recognition took decades. We said last time that he started from rules with nothing to look at. That's the whole reason his book sat unread. It's also the reason it worked, because a definition made of rules doesn't care how many components you have. 3 conditions about sums, and scalars run just as well in 100 dimensions as in 2. Nobody can draw 100 dimensions. That coldness on the page is the price you pay. Reach is what you get for it. As for which subsets of R3 pass, there are 4 kinds, and you can count them on one hand. All of R3. Planes through the origin, lines through the origin, and the set containing only the 0 vector. That's the complete list, and nothing else survives. Every item on it comes from one construction, and you already met it. A linear combination is any sum of scalar multiples of vectors. The span of V1 through V, P, is the set of all vectors you can write that way. Here's the claim. If V1 through V, P are vectors in Rn, then V equals the span of those vectors is a subspace of Rn. And we say the vectors span V. 3 conditions, 3 checks, watch how little work each one is. 0 equals 0 times V1 plus 0 times V2, and so on down the list. That's a linear combination, so the 0 vector is in the span. Take 2 vectors from the span. Say U is C1 V1 plus C2 V2 and so on, and W is D1V1 plus D2V2, and so on. Add them in collect terms. U plus W is C1 plus D1 times V1 plus C2 plus D2 times V2, and so on. Still a linear combination, so still in the span. Now scale take U again, and let it be any scalar. Then a times U is a C1 times V1 plus a C2 times V2, and so on. The coefficients changed. The vectors didn't, which means it's in the span too, so all three conditions hold. Done. Notice what that proof never touched. No arrows, no angles, no plane. It was arithmetic on the coefficients, start to finish, which is why it holds in Rn, where the picture ran out long ago. Last time, two vectors reached the whole plane, while another pair only managed a line. What in the numbers tells those two cases apart? Hamilton needed the words vector and scalar for a system of his own. The system faded. The vocabulary outlived it. Words are cheap. Coordinates are the expensive thing, and they're only worth anything if they're unambiguous. Think about what a coordinate is actually promising you. You give me a list of scalars, and I give you back a point. Now suppose two different lists land on the same point. The address no longer tells you where you are, and you can reach everything and still describe nothing. That's the real cost of carrying a vector you didn't need. Not clutter. Ambiguity. So what's the exact test for having no redundancy at all, and what's left standing once you strip it out? Bring in W again, a new vector under an old letter, minus 1.5 and 1, alongside our V, 3 minus 2. W is minus 1/2 times V. So the span of V and W is the span of V, which is the span of W. One line. Two dials, one direction's worth of reach. A set of vectors V1 through V, P is linearly independent if the only solution to C1 V1 plus C2 V2, and so on, equals 0 is the trivial one, every C equal to 0. Otherwise, they're linearly dependent. Test our pair. 1 times V plus 2 times W is the 0 vector. Those coefficients aren't both 0. Dependent and detected from the numbers alone, which is what we were after. A basis of a vector space V is a set of linearly independent vectors that span V. Not too many, because they're independent, and not too few because they span. Spanning says every vector in the space can be written as a combination of them. Independence says that writing is unique. A basis isn't unique. But every basis of a space has the same number of vectors, and that number is the dimension. So in a space of dimension n, any n independent vectors form a basis, and any n vectors that span it form a basis too. The plane was never a room you put vectors into. It's a set that survives its own two operations, and two independent vectors are enough to build every last point of it.